The problem we're going to dive into today is best understood through the lens of music. Suppose we had three notes that are played together as a chord. One natural way to represent this chord is through a plot of the amplitude of the sound signal over time. But in a practical sense, a representation that's much more useful when working with audio processing is just the underlying notes that make up the chord. Each chord is a distinct frequency, and having granularity on what frequencies are present in the original audio lets you unlock a lot of powerful tools. One especially useful tool in the world of sound engineering is an equalizer. An equalizer allows you to bring down specific frequencies, giving a new signal with a different sound profile. Conversely, we can also enhance frequencies that we'd like to bring out. An equalizer is just one of many tools that rely on a frequency representation of a signal. What you and I are going to talk about today is a small but essential piece of how this fundamental idea of representing a signal with its frequencies works. The core concept involves arguably one of the most important algorithms in modern technology, the Discrete Fourier Transform, or DFT. Most people who learn about the DFT for the first time often find it initially difficult to grasp. It's a complex topic that's hard to teach. The goal of today's video is to attempt to see if we can reinvent the clever ideas behind a discrete Fourier transform from first principles. On the way, we'll naturally interact with some of the fundamental concepts in digital signal processing. When discussing the topic of signals, most mathematical representations model them in a continuous time setting. Specifically, a signal could have a value for any real number time input. But in a practical sense, no computing machine can ever represent signals in this manner. So naturally, what we have to do is sample points from the signal. The most common sampling scheme is to uniformly sample these signals to get a sequence of points that represent the original continuous signal. But there's a lot of nuance involved in sampling continuous signals. Here's a fun thought experiment. Let's say I give you a cosine wave with frequency 7 cycles per second, or 7 Hz. How many points do you think we need to accurately capture this signal? Think about it, it's not an easy question by any means. Let's start by ruling out possibilities. Can we get away with representing the signal with 7 evenly sampled points? Well, one way to quickly see the issue here is if our sampling scheme happens to unfortunately sample every peak of this wave, the subsequent signal looks just like a constant signal. This, by the way, is commonly called aliasing. If we sample too few points, there are many possible signals that could produce the same samples that we obtain. Okay, so one way to think about this is we probably need to find a way to sample both the peaks and the troughs. So is there a way we can get away with sampling 14 points instead of 7? Funnily enough, there's a way to even break 14 points. If you happen to sample evenly, such as this, once again, you get a constant signal. It turns out the correct answer for this question is 15 points. If you sample 15 points in any uniform manner, you're guaranteed to accurately represent this 7 Hz signal. This is an example of a quite famous theorem in signal processing called the Shannon-Nyquist sampling theorem. There's a lot more material here that I'm purposely glossing over, but the important takeaway that I want you to remember is that for any signal of frequency f, we need to strictly have more than 2 times that frequency f sampled points to accurately represent the signal. Another equivalent representation is that given n samples of a signal, the highest possible frequency that could exist within the signal is strictly less than n divided by 2. Any higher frequencies are not guaranteed to be accurately captured. This will become important later, so keep this fact in the back of your mind. One cool example of this in practice is most audio sources have a sample rate of at least 44.1 kHz, and the reason why is the human ear generally can't catch frequencies above 20 kHz. These samples taken from the original signal give us a clear understanding of how the signal changes over time. Now what we showed with equalizers is another representation of the signal, but in terms of its frequencies. Fundamentally, these two representations give us the exact same signal. They're just two different ways of communicating that information. What this frequency representation tells us is that this particular signal is composed of 3 different waves of frequency 2, 5, and 10 Hz. The idea of this frequency representation is if we take these 3 waves, scale them by their relative strength, and add them together, we will get the original signal. This is the core idea of what's called a frequency domain representation. It's extraordinarily important that we understand that all the DFT involves is a conversion between a time domain representation to a frequency domain representation. Whenever we want to understand how we might rediscover a complex idea, it really helps to have an understanding of how we would like it to behave for some simple examples. Suppose we have a cosine wave of frequency 2 Hz. Ideally, what we would like the frequency domain representation of such a signal to be is a peak at the frequency 2 and zeros for all other frequencies. So in the context of this simplified example, we're looking for some operation that produces a high value for an input frequency of 2 and zeros for all other frequencies. So what that means is the operation we're looking for is fundamentally a measure of similarity. When the frequencies match, we should get a high similarity score, but when they have different frequencies, we ideally want our score of similarity to be 0. Given a sequence of input points from a time signal, we can essentially represent the sequence as a vector. Now, one of the most common ways to represent similarity within the context of vectors is the notion of a dot product. So let's start our analysis by seeing how we can properly construct a similarity measure for our original time domain signal and different frequency cosine waves. In order to properly construct a dot product, we need a set of samples from the cosine waves that we want to compare with. As a first attempt, it seems reasonable to sample the cosine wave at the same sampling rate as the original signal. And this does work well when the original signal and cosine wave match 1 to 1, as it does here in this simplified example. But what about other frequency cosine waves? There are theoretically infinitely many cosine waves that we could compare to in this time segment, and we can't evaluate all of them. So how do we go about picking a set of frequencies to compare with? To be clear, there are inherently 2 frequencies involved. One is the frequency of the original cosine wave, and the other is what we'll formally call an analysis frequency. For any analysis frequency f hat, we'll currently define it as a cosine wave with amplitude 1 and frequency f hat. So when picking frequencies we want to compare against, remember a key property we're looking for in our frequency domain representation is we want all frequencies other than the intrinsic frequency to have 0 contribution. So let's see what happens when we take the dot product of this cosine wave with other frequency cosine waves. Here we'll slowly adjust the analysis frequency and observe what happens to our similarity measure. One thing to notice here is that if you take any random cosine wave of some real number frequency, the contribution is actually almost always non-zero. But there are a specific set of frequencies where things just perfectly cancel out and we end up with a contribution of 0 as we desire. What's interesting from this particular example is that when our analysis frequency is defined such that there is an integer number of cycles within the time range provided, the similarity measure seems to always end up being 0. This looks kind of promising, so let's dive a little deeper into this behavior. So far, we've been quite hand-wavy with our treatment of what we're looking for in the DFT. To go one level further, let's formalize things a little bit more carefully. Right now we have a time domain signal which, as mentioned, can be represented as a vector of sampled points. We want to define some transformation that takes this time domain signal and gives us a frequency-based representation, where a certain set of frequencies is mapped to a value that represents a contribution of that frequency to the original signal. We already asserted that for a simple cosine wave with frequency f, how we want this transform to behave ideally is to have a high value for that frequency f, and zeros for all other frequencies. We saw some promising signs of this behavior as we compared our cosine wave to different analysis frequencies. Currently, we have a similarity measure that's defined as a dot product between our original signal and sampled points from an analysis frequency. And what we're looking for is performing this operation across a set of analysis frequencies. What sort of transformation operation expresses this really well? What we're essentially trying to define is a matrix vector product. By representing samples from different analysis frequency cosine waves as rows of this matrix, we get a compact representation of our dot product similarity measure applied to all analysis frequencies. What we're ideally looking for is three fundamental requirements to be satisfied in this specific example of a single frequency cosine wave. First, we want it to be the case that when the analysis frequency is exactly the same as our original signal's frequency, the respective frequency domain values should be greater than 0. And 2, when we compare against analysis frequencies that have some other value than the original signal's frequency, we should get a corresponding dot product of 0 to signify that there was no contribution of those frequencies to the signal. And lastly, we would like this transformation to be reversible. Given a frequency representation of the signal, we'd like to exactly reconstruct the original time domain signal. Now, it turns out these requirements can be translated to fundamental mathematical properties of matrices. Starting from the bottom, to make this operation reversible, this mysterious matrix must be invertible. And to fit these two constraints, what we're looking for is an orthogonal matrix. So immediately off the bat, we know that our eventual definition of the Fourier transform needs to have the same number of analysis frequencies as the number of samples in the signal. Otherwise, there's no way the matrix can be invertible. Well, let's see if our earlier definition of analysis frequencies for cosine waves fits the criteria we're looking for. As we have seen earlier, the nice property of these sampled points from analysis frequencies of cosine waves is that when the cosine waves have the same integer frequency, the dot product is non-zero. And when they have differing integer frequencies, they have a dot product of exactly 0. Or at least, that's what I implied earlier. Some of you may have noticed that this is actually not accurate. It turns out that there are particular pairs of analysis frequencies that have a non-zero dot product, even when the underlying frequencies are different. In fact, if we compute every combination of dot products between these analysis frequencies, we see an interesting pattern. For every non-zero analysis frequency, there exists exactly one other frequency that results in a positive dot product. What's going on here? Well, if we pull it apart, we see the problem is that even though these particular frequencies have different underlying cosine waves, the samples themselves are actually identical. This is essentially a byproduct of the Shannon-Nyquist sampling theorem. Since we're only sampling 8 points, any frequency 4 or above cannot be accurately represented with 8 samples, so we end up with overlap. One thing that you might notice here is that a subset of this matrix is nicely defined. And one way that we can sort of get past this sampling problem is to only consider the first half of any frequency spectrum. When we use this transform on any non-zero frequency cosine wave, there will always be some redundant information as a result of the nature of our current definition of the transform. The bigger problem here is because multiple rows of our analysis frequency matrix are identical, that actually means our matrix is not only non-orthogonal, it's also non-invertible. This is unfortunately a serious problem. Invertibility is an essential requirement so that we can actually reverse our transform. As a result, minor spoiler here, this is not the actual Fourier transform. But sometimes, from an engineering perspective, it's fun to try something that we know is wrong and see where things break down. Before we dive into how frequency decomposition via the DFT really works, I want to take a quick aside to talk about some similar types of activity that happen on a day-to-day basis. In some countries, it is legal to monitor your internet traffic and build up an online profile of you, basically taking in a signal that's a function of web activity and decomposing it into a fairly accurate advertising profile, one that can perhaps also be sold and used maliciously. When browsing online, this is not something any of us would like to think about, so that's why I recommend NordVPN, the sponsor of today's video. NordVPN prevents outside parties from intrusive tracking and building up such a profile. It's also great in areas where internet service providers can purposely slow down your connection. In addition to these essential features, one of my favorite uses of NordVPN is while traveling. NordVPN can give you a spoofed location in any of 60 countries, allowing you to get access to shows and entertainment that you may not usually get. The ability to connect 6 devices simultaneously allows you to take these features anywhere you go. NordVPN has been in this business for years, making it easier than ever to get set up. They've built a reputation that values trust and cybersecurity. If you're interested, go to nordvpn.com/reducible to get the 2-year plan with an exclusive deal plus 1 bonus month free. It's risk-free with NordVPN's 30-day money-back guarantee. Thanks to NordVPN for sponsoring this video. Going back to our previous question, we know our original transform has an issue with invertibility, and to see where things break down, let's observe what happens when we try to apply this fake Fourier transform to a variety of signals of different definitions. Let's think about some test cases. To set some ground rules surrounding our assumptions, all the transforms from here on out will be taken from 16 points of the original signal, and we simply display half of the frequency spectrum. This allows us to at least capture frequencies of up to 7 by the Shannon-Nyquist theorem. Let's start with what we've been doing so far, cosine waves. The first case is that we want any changes to amplitude to be appropriately reflected in the strength of the respective frequency in the frequency domain. And when we gradually change the amplitude of the original signal, we indeed see that this works as expected. Amplitude changes do seem to be properly captured by our fake Fourier transform. The next test case is to change the frequency of the cosine wave. What we expect to happen is that our test transform's peak will be correspondingly updated to the new frequency as our frequency changes. And indeed, that is the case. The peak moves in the frequency domain as the frequency of the original signal changes. Let's see what happens when we shift the y-intercept of our cosine waves. When we shift these waves up, we are essentially adding a signal of 0 frequency, and our fake Fourier transform does encapsulate that information in the contribution to the 0th analysis frequency. Alright, so far nothing has clearly been broken, so let's make our test cases a bit more complex. Here's a combination of different cosine waves, and let's see if our test transform properly extracts all the frequency components. We want our ideal Fourier transform to extract exactly these frequencies. When we pass the sampled point from the signal into our test transform, we do indeed get those frequencies. The fundamental reason this works is that our transform is just a matrix multiplication, so it's linear. What that means is the output of this transform on this aggregate signal is exactly the same as if we performed the transform on the individual signals separately and then summed the outputs together. So far, we focused on cosine waves. Let's now see what happens when we use sine waves. What we expect is if we pass in a sine wave of some frequency, we should ideally get that same frequency displayed in our frequency spectrum. So let's try it. What we get is a bit surprising. It seems like all the frequency components are 0. And if we do some further digging, it turns out that if we take the dot product between this cosine wave analysis frequency and the matching sine wave frequency, the dot product is indeed 0. And interestingly enough, this is true for any frequency. Sine waves and cosine waves of matching frequencies are orthogonal to each other. Our test transform as currently constructed will be unable to extract frequency information from sine waves. To understand what's going on, we have to go back to our test cases. We tested changing amplitudes, we tested changing frequencies, and we also tested shifting the signals up and down. But one other component of signals that we can change is the phase. Remember, what we expect to happen when we change the phase is that our frequency component strength should stay the same. After all, it's the same frequency still present in the original signal, just shifted across time. But what happens with our test transform is, unfortunately, the frequency strength is impacted by the phase. The sine wave example is just a specific case when the phase is offset by 90 degrees. So fundamentally, this is where our fake Fourier transform breaks. Let's now see how we can fix it. Well, in the case where we originally had a sine wave, one kind of hacky way to fix this problem is to use analysis frequencies that correspond to sine waves instead of cosine waves. Now with the sine wave version of the transform, every frequency sine wave properly gets a frequency contribution after going through our test transform. But as you may expect, this breaks our original cosine wave comparisons, where we now end up with the same problem. So there seems to be some kind of balance that needs to be struck here, but how exactly can we do it? Well, let's play around with these separate cosine and sine wave analysis frequencies and see what happens. Given a signal, let's modify the phase of the signal and capture values from both the cosine and sine versions of our fake transforms. What's going on here is we are capturing the dot product of the matching analysis frequency for our original signal for both versions of these transforms. As you can see, when the underlying wave is a cosine wave, the cosine component dominates. When the phase is altered to a sine wave, the sine component takes over. One thing that's kind of interesting here is these values are never simultaneously zero, and there's also a fun sort of dance going on between them. One idea that seems interesting is to see what happens when we plot these values on a 2D coordinate plane. And what's pretty interesting is we see that these coordinates trace a circle as we change the phase of the original signal. How cool is that? But the question remains, how do we put this together in a way that solves our phase problem? As a reminder, the original issue we're trying to solve here is as we were changing the phase of our signal, we were getting different frequency contributions from the test transform. What we want ideally is a way for our frequency contribution to stay the same regardless of phase. Can we use a feature of these coordinates that trace a circle to give us a value that stays the same regardless of the phase? As some of you might have already guessed, it's the radius, or more concretely, the magnitude of these coordinates. So let's put this together into a new proposed solution. We originally had a matrix containing analysis frequencies of cosine waves. Now what we'll add to the equation is a similar matrix, but for sine waves of different analysis frequencies. The big idea now is that we can apply the cosine wave analysis frequency matrix to give us x coordinates, and then apply the sine wave analysis frequency matrix to give us y coordinates. The final frequency domain representation will put these two coordinates together via the magnitude of these coordinates. Here's the final combined version of the transform applied to our previous test cases. This combined version of sine and cosine analysis frequencies, by the way, is what most people refer to when they talk about frequency domain representations of the true discrete Fourier transform. But the DFT uses one more trick to simplify things. After all, generating these two matrices, performing this transformation twice, and then extracting the magnitude is a bit convoluted. The key insight is instead of keeping track of two matrices that have sampled points from cosine and sine waves, we can jointly represent the two coordinates as sampled points from a unit circle into a single matrix. So let's see how this actually works for a signal with 10 sampled points. Breaking down an example is one of the best ways to see the underlying pattern. For the analysis frequency 0, all the points are simply the same coordinate. It's a zero frequency signal, so this is expected. For the analysis frequency 1, things get more interesting. If we plot the corresponding points from our cosine and sine samples, we get the following 10 points. And intuitively, what's going on here is we're taking a single cycle through the unit circle and uniformly sampling points until we get 10 points. For the analysis frequency 2, the points from the sine and cosine waves align as follows. And once again, a nice way to interpret this is we are regularly sampling points from the unit circle, but now the key difference is we do it over 2 cycles. Let's do analysis frequency 3 to make sure the same pattern holds. We plot the sine and cosine points as before, and what we again see is that they are uniformly sampled points from the unit circle with an underlying frequency of 3 cycles. This pattern actually ends up continuing over all analysis frequencies. The key interpretation here is that each analysis frequency samples points from the unit circle in a uniform manner with an angular frequency that matches the analysis frequency. The final part of the simplification to the true DFT is when we discuss points on a unit circle, it's quite convenient to represent the coordinates as complex numbers. The real components of these complex numbers correspond to points on the original cosine wave, while the imaginary components are mapped to points on the original sine wave. In practice, these points are compactly represented as complex exponentials via Euler's formula. The final DFT matrix is composed of complex exponentials, where every row corresponds to sampled points from the unit circle at distinct integer analysis frequencies. One of the most mind-blowing facts about this DFT matrix is by defining it as complex exponentials regularly sampled from the unit circle, it's actually an orthogonal matrix. This matrix, as a result, ends up satisfying all the requirements we were looking for when we started this journey. So taking a step back, the DFT is fundamentally just a matrix vector product of a time domain signal with the DFT matrix. When you multiply this matrix with your time domain signal, you get a sequence of complex numbers. The magnitude of each of these complex numbers tells you the contribution of that respective analysis frequency throughout the original signal. The angle of the complex coordinate is a measure of the phase of the signal. The best way to see this is with our previously failing test case. When we perform the DFT transform and plot the magnitude of the frequency components, we can see that the magnitudes of the peaks do not change as the phase of the signal changes. But what's really cool is the angle of these corresponding peaks, when plotted on a complex plane, correspond exactly to the phase of the signal at that frequency. This is how the DFT uniquely captures frequency contributions and phase in a signal. Earlier we talked briefly about how there are two peaks in the full spectrum of a cosine wave when using our fake transforms. The true DFT also has this property for real valued cosine waves. But now the interpretation is a bit different. The DFT decomposes a signal into a set of complex exponentials. The first peak corresponds to a complex exponential that has an underlying frequency matching the original cosine wave frequency, while the second peak corresponds to a complex exponential that has an underlying frequency that is moving in the opposite direction and perfectly cancels out the imaginary component of the first complex exponential. And this will always be the case for all real valued signals. This symmetry is required to cancel out the imaginary components and get a real signal. A final example that's also helpful to gain intuition on what's going on in the DFT is notice how as we change frequencies of our test signal, when the test signal matches one of our analysis frequencies in our DFT matrix, the values from the respective analysis frequencies shoot out, while all the other frequencies are centered around 0. This is another way to visualize how our earlier measure of similarity materializes now in a complex plane. From an implementation perspective, the DFT is fundamentally just a matrix vector product, and the inverse DFT to get the original signal back is also a matrix product, with the inverse DFT matrix multiplied by a frequency domain representation. Most of you could probably implement this matrix vector product yourselves, but in practice, the true DFT is computed using an algorithm called the fast Fourier transform. I have an entire video on this really elegant algorithm that I actually approach from a completely different perspective. Part of the reason I wanted to make this video is that there were so many great comments from the previous video on wanting to understand the DFT in a signal processing context, and I hope this video delivers on that. So even though the DFT does get a bad rep for being quite complex, pun intended, at the end of the day, by going through a kind of playful process of trying different ideas, even with a lot of hand-holding, I'm hoping you come away from this video with a sense that there's a logical reason for why it's defined the way it is. Most of the time in computer science, there's so many abstraction layers that you deal with. For example, you can utilize the DFT using a single call to an FFT function and somewhat get away with not really understanding what's going on underneath the hood. And honestly, that's completely fine. Abstraction is so important in terms of just being able to focus on what you need to accomplish. But I do think that peeling away the abstraction layers behind how some of these concepts work holds some of the most beautiful ideas in computer science. Thanks for watching, and I'll see you all in the next one.